I'm going to ask you guys what you think about this graph right here, what it appears to be to you. Like if this were a quiz or a test question and I said, write the equation of this graph, what would you write? Y equals x. Okay, so what would be your reasoning for saying that? What do you see? What characteristics tell you that it's y equals x? Yeah, Drew.
Goes to the origin, so it's linear and goes to the origin, so it got tangent of the value, and so it's linear, it's y equals x.
Yeah, so clearly it goes through the origin. You can see that, right?
And the slope.
Slope, I think you could reasonably say it looks like it's 1. Okay, yeah. And you said it's linear, right? So I think all those things would add up to mean y equals x. Tess?
What's the window?
Right. Yeah, that could make a difference. Let me do a little bit of messing around with this really quick. I've got my calculator screen here, and what I'm going to do is I'm going to trace this. So the obvious answer to what is this a graph of is y equals x. And so with y equals x, doesn't the output always match the input? Like 1, 1, 2, 2, 3, 3, 4, 4, so on and so forth. So I'm gonna hit trace here. I already did, I guess. You can see x equals 0 and y equals 0. And I'll start scrolling to the right. And immediately you can... Oh, wait, hang on. Oh, never mind. Let me get to this. There we go. Immediately, you can see that Tessa's question of how big is the window is pretty valid. Because I scroll to the right, and the x value and the y value are the same, but they're really tiny. 2.36 times 10 to the negative fifth.
Well, basically 0.
Just a little bit bigger than 0, right? Okay, so I keep scrolling to the right. You guys just pay attention, please. Just watch the x and y value. They should match. If it really is y to the x, this just could be a zoomed up picture of y equals x. Keep going here. They match. They match. It's looking pretty promising. Numbers are still really tiny. We're talking times 10 to the negative fourth. Talking about thousandths of a unit here. Boy, yeah, they're looking pretty good. They're all the same. All the same. We just keep cruising along in here, and it looks at least... it looks through at least, intuitive, or I should say inductive reasoning. It looks like, yeah, this has got to be y equals x. Just keep moving along here. I don't know. I'm just making sure. Glad you're entertained. I'm entertained. Watching all these numbers go by. There's a point to this. Hey, we're not in the times 10 to the negative anything, right? So the numbers are getting a little... Oh!
Yes.
Oh, 1.
Do you see it? Do you see it? JJ, do you see it? Can you stop hyperventilating and see it? Do you see how now, right now, the x and the y are a little different, aren't they? Yeah. Remember I told you had to play along. I hope you're playing along. Oh, now they're back to being the same. So maybe that was just a glitch. Who knows? Back to being the same. Look at that. Maybe that was just a glitch that caused Jared to have some issues there. Huh. Still the same. So maybe it's just like it was 1 point. Very interesting. Keep going here. Keep going. Keep going. Look at that. They're all the same again. I'll just keep scrolling across the screen here.
What is this?
So interesting. Oh, different. Same.
Wait, what?
Wait a minute. Yes, what's going on? All I'm doing is I'm scrolling to the right, looking at my x and my y coordinates.
That's one does. I'm trying to think of how I can relate this.
Hey, remember I told you at the start, you can get a lot out of this or a little bit, depending on how focused you are. So I would stay focused. It's okay to giggle and laugh. About what? I have no idea what you're giggling about. Interesting. There's another different one. Why are we getting all these values that are different? What would be your proposal? Say again? My calculator's dumb. Well, that's possible. I'm just getting a bunch of the same ones again. Oh, different, same, same. Bunch more of the same. Same, different. The differences are coming a little more frequently, though, aren't they? Before, it was a long space between the numbers that were different. Back to the same, same,
The difference between a normal.
different. Huh. Oh, my goodness. Very different now. I'm scrolling way to the right. Okay, same, different. I'm just looking at the end digits. That's really all you really need to look at. Different again, right? 5.2 versus 5.1. So, you've seen a lot of examples where the x and the y coordinates didn't match. So does this support the idea that this is really y equals x?
No.
So if we actually, you watch, no magic here. You can see my button pushes here. I'm just going to go zoom 6. And you can see what it really is.
Fine.
Good guess. It's really y equals sine of x. Y equals sine of x. So if I bring this screen back up, you can see that it was up here. You can just see that it was y equals sine of x the whole time. But we have just zoomed way in. So I want to take you way back to what we talked about towards the start of the year, and really for AD students frequently through last year as well. Any function, this gets to Tessa's point earlier, I think, that any function, no matter how curvy it might be when you look at it from, step back pretty far, if you zoom in enough, it'll always look like a line, called local linearity. So no matter how curvy a graph is, just keep zooming in, and eventually it'll look like some kind of a straight line. So we were looking at it really closely. In fact, we were very much zoomed in right here around the origin, which you can't see my mouse. So if I were to zoom, if I was going to do one of those zoom boxes, I could draw a little box right around here.
Wait, what is that function?
You can just draw a box around what you want to zoom in on.
That's not what I'm talking. How did you do that?
Oh, it's acting kind of weird right now.
How did you zoom? What? I've never seen that before.
You've never seen zooming in?
Zoom box. I've never seen that before.
Well, it's not working very well right now, so I don't know if this is going to be a good example. I don't know, it's acting really weird. Anyways, so there's a point to this. Wouldn't it be fair to say that if you are zoomed in ultra close to the origin, that y equals x is actually a pretty good representation of sine of x? Pretty good to the point where, I think any reasonable person would have said y equals x when they first saw that graph. So I want to do this. I want to just draw that in. So I'm going to put this in red. I'm just going to write y equals x, and I'm going to hit graph. I'm going to change my window just a little bit, just so it'll be a little easier to see stuff. I'm going to go -7 to 7 on my y's, and I hit graph. So here is sine doing its thing. Here comes y equals x, and you can see right there around the origin, that's pretty darn good, isn't it? It's only if you're zoomed way in. If you look at it from this perspective, step way back, you look at it, well, it's actually a horrible representation, isn't it? But if you zoom in real close, and so when I say zooming in really close, I'm going to start referring to how close we need to zoom in, that we call like an interval of convergence. Like, how close do you need to get for this thing to look good? Okay, so I'm going to just write on the, I'll write on the screen. I think I can do that. You know what, it's going to be easier to write on the board. So folks watching the video are just going to have to imagine with us. So what I'm going to do is I'm going to draw a little mark right about here and right about here. Would it be fair to say that that is where, between those two marks, the red graph is a pretty good representation, / very good, right? It seems to really closely coincide with the blue graph. Is that fair? Okay. If we were to say, hey, the red graph, the line y equals x, is an approximation for the blue graph, which is y equals sine x, it's just an approximation, right? That means it's not exactly perfect. So something that's an approximation will have an error associated with it, right? That make sense? So what I want to do is I want to graph the error. The way that you find an error is to take the actual value minus your approximation. Right? Actual value minus approximation. So what I'll do here on the calculator is I'll go back to my y equals, and I am going to, in my third equation, I'm going to put y1 minus y2. So it's going to look like this. Variables, y variables,
Why does not put sine of x minus x?
because things are going to start changing here in a second. You'll see. That would normally be a good strategy, but I'm going to do it this way for now. This will give me a lot of flexibility. The other thing I'm going to do is I'm going to turn off graphs 1 and 2. So I know that graph 1 is sine x. I know that graph 2 is x. I know that graph 3 is sine of x minus x, right? So this will represent the error. But I'm going to turn off y2 and y1. So I just highlighted the equal signs. Now those are not going to graph. The only thing it'll graph is y3. So I hit the graph button now. I get like a really interesting graph. So that represents the error. Like if I use the line y equals x to represent sine of x, that represents the error. And I want you to see, if you look up here, these are my two little marks that represented my interval of convergence. And if this represents the error, out here doesn't this mean the error is really big?
Yeah.
And the error is really big?
Yeah.
Since this is like right on the x-axis right there, doesn't that mean the error is really tiny? Slash almost zero? So this is really good, right? This is saying the error is really tiny right there. This is not so good of an approximation. This is not so good of an approximation. So if I know what my error is, then if I just took that error and added it to my approximation, wouldn't that make my approximation better? You see what I'm saying? Like if I told you, if I said, hey, guess my height, and you said 5'10", and I'm like, yeah, you're really close, you're off by 1 inch. Well, that means you either need to go +1 or -1, right? 5'9", right? So your approximation would go from to much better if I told you your error. That makes sense? So, what does that graph remind you of, sort of, as far as like a regular old polynomial graph? What does it kind of look like?
X squared.
Cubic. So here's what I'm going to do. I'm going to think about if I could take a cubic, it's cubic-ish looking, right? At least around my interval of convergence. I'm going to add a cubic, a certain cubic on, but isn't this one of those negative cubics? Right? This is one that decreases from left to right. So I'm going to go back to my y equals, and I am going to turn off my error graph, and I'm going to turn back on the y1 and the y2, but instead of just having y equals x for my approximation, I'm going to take Hayden's idea and say, well, why not y equals x minus x cubed? So all I'm really doing there is I looked at my error. My error looked sort of like a cubic, and I'm like, all right, well, let's just go ahead and plug that into, on top of my approximation, because if you have an approximation and you know the error, you just add the error on, and you should have a much better approximation. That makes sense. I'm trying to speak very general. Like this doesn't really even have to do with math necessarily. If you know an approximation, you add the error. If you know the error, it should give you a much better approximation. So here's my graph. So there's sine, just like it always was. My new approximation shouldn't be a line anymore. It should be a cubic. And there it is. So, what do you guys think? Is this better, worse, same?
I think it's a little better.
It's a little bit better. And I'm looking at my marks here. I mean, you could almost argue, to be honest with you, you could almost argue that my interval of convergence is almost a little worse, isn't it? I mean, I don't know if you guys can see it very well from there, but it looks to me like right there and right about there is where the two graphs seem to separate out a little bit. What could we do to the cubic? Make it a little bit better. Better approximation. How could we widen out the interval of convergence? Because the wider that interval of convergence is, the better our approximation. How do you widen out a cubic? Say again? Times it by what? numerical number? Like, you be specific?
Like 2 or 3.
So multiply the whole cubic by 2 or 3. So let's see here. Let's go back. So, you think we should multiply the whole cubic by some number? Or how about, I don't want to take you too far down a rabbit trail. What affects, I guess I'm asking you guys to recall like pre-calc stuff, right? Like how do you make a cubic fat? You do multiply by a number, sorry? A fraction, but do you multiply the whole thing by the fraction? Just the lead, right? Just the lead term. So, what fraction do you think? So, it's not going to be a 2 or a 3. 1/2. Okay, fair enough. So, I'm going to go insert.
How do you do that?
Glad you feel so passionate.
Where have you been? Never inserted?
No, I have to erase it and then start over.
You go second, and then right above delete it says ins, which stands for insert. Okay, so we did 1/2. It should be okay. Parentheses would be fine too, but it should be okay. Okay, so I hit graph. And so this should have widened the cubic out. Let's see if this was good enough for you. It's definitely a little better, isn't it? Do you think it could be better yet?
1/3.
1/4, 1/3, 1/6. I mean, all kinds of numbers here.
1/1000.
1/1000.
1 over pi. 1 over pi.
Oh, I like
So let's
this
see here.
idea. 1 over pi.
Let's just run through these really quick. So 1/3.
I don't know.
I don't know, it just sounds cool.
I heard 1/3 out there, which makes sense because it's a little smaller than 1/2. So that's going to make it a little fatter. And that's definitely, can you see the difference there? That made a difference. I heard 1/4, so let's take a look at 1/4. It seems like pi should be in there, but let's just stick with nice integers. Okay, 1/4. Jasper, are you watching? Watch the magic. Come on. This is one of the few times in this class where I'm just going to ask you guys to watch and listen and talk instead of write. Just watch. That got better, didn't it?
1/6.
I heard 1/6. Let's take a look at 1/6.
Let's go 1/7.
I'm just going to go in order of things I heard. So 1/6. I hit graph there. So it should be better yet, right? That is better, isn't it?
Ooh.
So I heard 1/10. I heard 1/1000th actually. Maybe that's right. So let's go 1/10. Who knows what this will look like? So Hayden, once again, we're going to go 1, second, insert 0. Look at that. And then graph. See what happens here. Ooh, that's kind of interesting. What do you see happening now? Wasn't it too wide now? So 1/10 is too wide.
Let's go 1/7.
1/7. Okay. 1/9 would seem like that's reasonable. I'll go with 1/7 here. See how good this looks. 7, delete, graph. 3 pi, that sounds even better. You're sounding super official. Okay.
1/8.
1/8. Okay. I don't know if you guys are too far away. Maybe you aren't. Can you see that little spot there?
Yeah.
And that little blue spot peeking out?
2 pi. 1 over 2 pi.
Kind of interesting. 2 pi. I heard 8. 2 pi. That's an interesting idea. I'll go with 8 first. Everything has to have a pi in it. Okay, so 8. Graph. Let's see what this looks like.
You know the best number?
Can you see?
9 3/4.
Can you see the blue peeking out?
Did it.
So again, this is a little too much. 2 pi is going to be really interesting. I don't know how that's going to
Lucky 777.
look like. 777.
7.77.
Okay, so we got to have parentheses here. So parentheses, insert 2 pi. All right, so we graph this. This is probably going to be hard to distinguish graphically, whether this is best or not.
It's really, really close. 9 3/4.
Yeah, that's really hard to distinguish. So haven't we, let's think about what we've established. Have we not established that like 1/3 and 1/4 is not small enough of a fraction? But like 1/8 or 1/10 is too small, right? So it's got to be in between there somewhere. We could tighten it up maybe a little bit better if we maybe tightened up our graph and zoomed in the window appropriately. This is going to be really hard to tell. So 2 pi is like 6.28, right?
Yeah.
Roughly. The truth is, the perfect number for this particular term is 1/6. 1/6 is exactly right. And I don't know where Chandler came up with that. He's been looking ahead in the notes or something. No? Okay. That was an excellent guess, Chandler, I must say. So we'll talk about why that is here in just a second. That's why I was going to say 2 pi is really close. It only is off by 0.28, so it's probably going to be really tough to tell the difference between the two. So I'm going to hit 6, delete, delete, delete.
9 3/4.
No, it's 6. 6 is the best number there. Okay, so let me go back to the graph here real quick, and I want to look at the interval of convergence. And the interval of convergence has widened out significantly. So when we just had y equals x right here, that was our interval of convergence. I would say now it's like maybe here and here. That's widened out quite a bit. That's pretty good. I imagine we could do a little bit better if we could find our new error.
Oh my gosh.
So here's what we're going to do.
I like this game.
Infinite summation?
So what I'm going to do is I'm going to turn off y1. Oops, that's not what I wanted to do at all. Let's do this.
Wait,
Turn off y1,
what did it mean?
turn off y2, and I'm going to turn my error back on. Make sense? So the error is now y1 minus y2 like it was before. So here we go. We graph the error.
Did you take a haircut? I can tell you my name.
And check it out. Do you see how my interval of convergence that I had up there corresponds with the error being roughly 0? Pretty close. But then as you can see, just kind of like before, we got a massive error out here to the left and the right. The error goes way off the charts pretty quickly. So once again, the idea is if you have an approximation and you want to make the approximation better, if you just had a way of kind of knowing something about the error, couldn't you just add that error back on and that would make your approximation better? So, what does that look like to you? Looks like a cubic, doesn't
Or
it?
tangent.
Looks sort of like a tangent.
It's like
Agreed.
really bad.
Can we rule the cubic idea out? Because wouldn't the cubic just be a like term with our previous cubic, which would mess up the
I think
1/6
the
thing?
fat
Like the
tangent.
next odd numbers away from the fifth.
So a fifth power polynomial can look an awful lot like a third power polynomial. It just gets fatter. And wouldn't you, I mean, if somebody asked you to describe this in terms of a cubic, wouldn't you say this is like a fat cubic? So a fifth power polynomial can very easily look like a fat cubic. So instead of adding a tangent on there, which I think I can reasonably see why you'd say that, let's go with a fifth power. I think Will is starting to see a little pattern develop here. And it's a positive fifth power, right? So I'm going to go back in here. I'm going to turn the error off. And I'm going to come back up here to my approximation, turn that back on. And I'm going to go plus x to the fifth. Come on, there we go. Plus x to the 5. And I'm going to turn on the y1 again. And I'm going to graph.
Why is that plus when the other one was minus? Why did you like?
Um, because exactly, yeah. So when we did our first error, you know, it kind of looked like this a little bit. So it was going downhill from left to right. And then the one we just looked at looked like this. So going uphill from left to right, so plus instead of minus. Yeah, go ahead.
Why do you keep like adding and subtracting all together?
So, okay, this is really getting at the heart of what I want you to get out of this. So when we first started off, way back at the start of class, I proposed to you the idea, using the graph, that y equals x was, depending on your definition of okay, like an okay approximation for sine of x. But what I said was, okay, if it's an approximation, by definition, an approximation is going to be off, right? And how far off it is what we usually call an error. So my proposition to you guys was this. If I have an approximation, and then I have some idea about what the error is, if I take my approximation and I add my error to that approximation, wouldn't that remove some of the error?
Yeah, so that keeps working however many times you do it.
Yes. What we're trying to do is we're saying, okay, at the start our error was this big. And then we added on something about the error, like we had a little information about the error. So now our error went from this big to this big. And then we like reevaluated our error. And I'm like, okay, our error actually kind of looks like this now. So if I add what I know about the error now my overall error is this big.
So when you keep adding terms, it'll never change anything that you've already added beforehand.
No. It'll make the overall number, like in the end, different. But have you noticed how the interval convergence went from like this wide to this wide?
Yeah.
So that's telling me that my approximation is getting a little bit better. A little bit better. So each time we add on like our newest knowledge about the error, we add that on.
Okay.
It makes the interval of convergence wider and our error a little smaller.
Okay.
Make sense?
Yes.
Okay. Okay, so we're gonna look at this graph here. Here's sine for the 1000th time. It seems like there's sine again, and showing up here should be our approximation.
I have an idea.
Whoa, hold on. Before we get to your idea, I just added x to the 5th on there, and you can plainly see that my interval of convergence has gone from this to smaller. That's not good.
Can you make it one?
We need to make the 5th power fatter. How do we make a 5th power or a 3rd power or a whatever power fatter?
Well, my idea was that what if we use sine of x to approximate sine of x?
No, just no. You'll see the point of this later on, hopefully. We got to make this approximation a lot fatter.
1/6.
1/6, okay. So let's see here. We're going to go insert 1/6. Okay, so let's decide if this was enough. Or if it was too big. Remember we went too far last time. Too far. Approximations coming in here.
Not enough.
That's not enough, right? We want our interval of convergence hopefully to widen out.
1/9.
1/9, 1/10, okay. So let's check it out here. 1/9. 1/9 graph. That's not enough, is it either?
1/12.
Say again?
1/12.
1/50th. 1/12. Whoa. We got some hugely different numbers here. Let's go. You said it first, Chandler. Let's go with 150.
I'm thinking that's going to be a bit too big.
No, that's perfect.
All right. Maybe Chandler has done some messing around with his calculator there just to see 150th. Definitely going to widen it out. There's no doubt. It's just a question of did it do it too much or is it just right?
Whoa.
Mm.
Oh, sweet.
That helped a lot, didn't it?
Oh, gosh.
That helped a whole lot. I mean,
How
That's-
did you won't know.
really good.
How did you know?
I'm curious, why did you come up with that number?
Well, 1/50 was too small, so I tried 1/100, and that was too small.
Okay.
And I tried 1/200, and that was too big.
Okay, yeah, very reasonable, very reasonable. So the truth is Chandler has come pretty close. He really has. It's a little too large on the denominator, but it's close. It's actually 120. 120. So 150 is pretty darn good though. Hard to deny that. So we were definitely playing in the minor leagues, right? Going with like 9, 10, 12. Chandler put us much closer. It's actually 120. These numbers are not random. I'm wondering if anyone can see the pattern in the numbers yet.
It's times 20.
It is a factorial. So this is the optimum. This is the optimum approximation. You can see with this
Oh!
that our interval of convergence is now right about here to here-ish. So
Yeah, makes sense. Do the math.
right about there.
Yeah, I would do that.
So Will brought up the idea of factorials.
She's fine.
So 6 is really
Oh,
yeah.
3 times 2 times 1.
3 factorial. 120,
5
5 factorial. Are you notice anything interesting about the exponents and the fractions factorial thing? Did you notice it was x to the third and it was 1 over 3 factorial? X to the 5, it was over 5 factorial. If you had to venture a guess as to what would be the optimum term next, what would you say?
7 factorial.
Minus.
That's right. So I'm going to go, it would be minus, wouldn't it? Are you seeing the alternating pattern here? So it would be minus, I'll just write it like this, x to the 7th
Over 7.
over, 7 math, oops, it's PRB, prob, right? There we go, 4. Okay. So now we graph it, and we should see an even better approximation, perhaps for the last time, for the moment at least. There's sine, and there is our 7th power approximation. You see how the interval convergence widened out even more. Yes, wow is right. So if you just zoom in right there from essentially negative pi to pi. So if I were to mess my window around here a little bit, and I just did negative pi
I knew the pi was coming up.
to, yeah, it had to come in somewhere, right? Negative pi to pi, you look at these two and it's almost perfect, right? It just maybe at the very end seemed to be differing a little bit. But it's really good. So we've gone from like very much of like a super rough approximation using a line to approximate sine. And now we've added a bunch of terms onto the end of that line, turning it into a 7th power polynomial. And now it's hard to distinguish between the two on that whole interval negative pi to pi. No longer do we have to zoom way in order for it to look good, right? Looks good even zoomed out a little bit. So I hope you see the pattern. If we continue on, we would add a 9th power, a 9th degree term, and then an 11th, and then a 13th, and a 15th. Where we're going with this eventually is how many terms would you need to make it perfect?
Infinity.
An infinite number of terms. So as the number of terms goes to infinity, you would actually find that the interval of convergence for this would be from negative infinity to infinity.
That's why I said we're approximating sine with
You're approximating what?
sine with sine.
Sure. Yeah. We're gonna go deeper than just saying that, though, right? But it'll end up being a perfect approximation. Not everything will have a perfect approximation. We'll talk about those as well. We'll maybe do another little exercise with this tomorrow. But I hope that was fun for you. It was fun for me just to watch you guys coming up with some good stuff, and you did. I mean, Chandler's idea was, I think, excellent as far as figuring out what that coefficient needed to be. This is where we're headed. One thing I do want to draw your attention to, though, as we went through that whole process of error, I want you guys to recognize something that we've already talked about that I hope will be a good connection for you. Do you guys remember we've talked about the alternating series and the alternating series error bound? So I want you to think about what we just did. I taught you guys, I think you guys started to buy into the idea that with an alternating series, the maximum error is less than or equal to what? Yeah, the first term that you left off. So did you notice that every time we added a term on, weren't we adding just like the next term? Didn't we essentially equate the next term with the error? And so you add on a term, well, you just took care of some of the error. You add on another term, well, now the error just got smaller. And this is an alternating series, plus, minus, so that you can make that connection, really saying, hey, we're just adding on what the alternating series would tell us is the next first neglected term. That would be the biggest possible error. So by adding that on, we just reduce the error to something less than what it was before. Okay? So we'll explore this. This is kind of the whole point of why we've been studying series. And we'll develop this out a lot more in coming days. So nice work.